All right, this is going to be the second year-end review video. I don't know if we'll totally get done today, but we'll see. So, let's imagine we are rolling a dice, and we're going to roll a dice 400 times, and we're going to add up all of the numbers on the dice. So what goes in my box? The numbers 1, 2, 3, 4, 5, and 6. And the number of draws is going to be 400. What is my expected value? Well, I need to know what the sum of the box is. So that makes 10. Those make 10. So 21. So the sum of the box is 21, which means that the average of the box is going to be 21 divided by 6, which is 3.5. I'm also going to need the SD of the box. And there's no shortcut on this one. So 1 through 6. And the SD is 1.707. So the SD of the box is 1.707. So how many points am I expected to earn? How would we get that? The average times the number of draws. So each draw is essentially worth 3.5 points. So 400 times 3.5 is 1,400 points. Okay. So what is the chance of scoring, let's say, what's the chance of scoring more than, so what if my score is greater than 1,500? How would I do that? Well, 1,400 goes in the middle, plus or minus what? I need a standard error. Which standard error am I going to use? SEN, the number, or sum. So that is, so the SEN is the SD of the box times the square root of D. So I'm going to take 400, or the square root of 400 is 20 times 1.707. So 20 times 1.707, and I get 34. All right, and I put a mark at 1,500, and I want to shade to the right. So 1,500 minus 1,400 is 100. So 100 divided by 34 gives me 2.94, and then I'm just going to shade norm from 2.94 to 5. And there is a less than 1% chance, a very low chance that that's going to happen. Okay, so that's how SEN works. All right. What if instead of wanting to know how many points I'm going to score, what if I wanted to know my expected value for the average? So how many points am I going to score per roll? What's the expected value of that? Well, I could take 1,400 and divide it by 400, but I already know what the answer is going to be. It's going to be 3.5. If you draw from this box, you are expected to earn 3.5 points per roll. So no matter how many rolls you do, you should get 3.5 as the average. So this is 3.5 plus or minus. How do we calculate the SE average? So SE for average is the SD of the box divided by the square root of D. Okay. So this will be 1.707 divided by 20. 1.707 divided by 20. And I get 0.085. Okay. So what is the chance of getting my observed value being less than 3.5? Wow. 0. Well, let's that's kind of weird. Let's change this to 121. So I'm going to draw 121 times, and I want to know what should happen. So this is going to be 1.707 divided by 11. And I get 0.155. So what is the probability of getting an observed value that is smaller than 3.6? Let's not do that. 3.52. So I draw my normal curve. 3.5 goes in the middle. And I'm going to draw a line at 3.52. And this is plus or minus, what was it, 0.15? 0.16. So 3.52, whatever, that'll work. So 3.52 minus 3.5, and I divide that by 0.16. So what am I going to plug into my shade norm? What's the lower bound? -5, so I covered it over. But I want this here. So from -5 to 0.125. And that probability is going to be about 55%. Okay. All right. What if I want to count sixes? I have to do a counting box. What is the counting box going to look like? 1, 1, and 5 zeros. Right? So, I can either do number of sixes or percentage of sixes. So maybe I'll do both. So let's say that we're going to play 225 times. What is the probability that our observed value is greater than 40 sixes? Well, what is my expected value? The sum of the box is 1. The average of the box is 1/6. Everybody good with that? What about the SD of the box? Do I need to plug this? Do I need to plug the zeros and ones in my calculator? No. I can do the shortcut. The shortcut is big number minus small number times the big fraction, which is 5/6, times the small fraction, which is 1/6. And this is essentially just 1. So we'll take the square root of 5/6 times 1/6, and I get 0.37 is my SD. Okay. So my expected value is 225 times 1/6. 225 divided by 6, we get 37.5. So my expected value is 37.5 plus or minus this number, What SE do I use in this case? SEN, SEP, or SE average? We want to know the total number of sixes. So SEN. So I'm going to times this by 15. Well, the square root of 225, which is 15. So 0.37 times 15 is 5.55. And I want to know what's the probability of getting greater than 40. So here's 40. I'm going to shade over here. 40 minus 37.5 is 2.5. So 2.5 divided by 5.55 is 0.45. And now I shade norm from 0.55 to 5. 29%. Everybody good with that? All right. So 1/6 is about 16.6.7%. So what is the probability of getting an observed value that is less than 18% sixes? So what is my expected value? Expected value is just the percentage that's in the box. So we could say 1, 1, and 5 zeros. We could also say 0.167 ones and what would that be? 833 zeros. That is a box that will also work. So my expected value is just 16.7%. Okay? And my SD is not going to change. It's still 0.37 because it's the square root of 0.167 times 0.833. And we got that in the last version. So now I need an SE average. So I divide this by 15. So 0.37 divided by 15, and then I change that to a percentage, 2.5%. Does everybody follow? Okay, so I draw my normal curve. Oh no, this should be attached to that. So I expect 16.7 plus or minus 2.5, and I want to know smaller than 18. So 18 minus 16.7 is 1.3. So I'm going to shade norm from -5 to 1.3, whatever that is. Okay. Is this helpful? Yes? All right. Let's say we are playing roulette and we want to know what's the chance of getting let's say we want to play green. So we want to spin the wheel, let's say 81 times, and we want the chance of winning money on green. How many numbers are on the roulette wheel? 38. How many of them are green? 2. So there are 2 ways to win, and we're going to bet $1 each time. So there are 36 ways to lose, and each time we lose $1. So how much are we going to win on green? You should be able to calculate that looking at this. The sum of the box is always -2. So how much does green pay out? $17. Okay. So if we bet on green, we expect to lose $2 every 38 times we play. So we divide that by 38, and I get the average of the box is negative 0.0526. Okay, so if we play 81 times, 81 times this is negative $4.26. So negative 420.26 plus or minus. What SE are we going to use in this case? Are we doing percentage? No. Are we doing average? No. We're doing total winnings. So SEN. So we're going to times this by the square root of 81. Nope, no, not that. I need the SD. So 17 minus negative 1 times the square root of 2 over 38 times 36 over 38. So that's 18 times this. So 18 times the square root of 2 38 times 36 38. So my SE is 4.02. And I want to know my chance of winning money. So I put a 0 right here, and I want to shade to the right. Okay. But I have to be a little bit careful here. I need to use edges. Why? Because I have fewer than 100 draws, which means my columns are sort of wide. So the original question said, what is the chance of winning money? So from 0, am I going to do the right edge or the left edge? Winning money. The right edge. How come? So if you get a negative value, did you win money? No. If you get 0, did you win money? No. So the question we're asking is, there's a box right here that has a left edge and a right edge. So we need to decide, are we using the left edge, which would be negative 0.5, or the right edge, which would be 0.5? And the question said winning money. And if we had more than 100, those columns are so narrow, they don't really matter whether you do edges or not. But because we're only playing 81 times, we need to use edges, and winning money would be from here over. So we need to go from 0.5. So 0.5 minus 4.26, or sorry, nope, minus negative. 0.5 minus negative 4.26. And we're going to divide that by 4.02. That's my z-score. So I'm going to shade norm from 1.18 to 5. And that will tell me the probability of winning money. Does that make sense? Okay. All right. We better do a little bit of probability stuff before we get into hypothesis testing. All right. Let's say I have a bag with 2 red, 3 green, and 4 blue marbles. Okay. What is the probability of reaching in the bag and drawing out a green marble? 3 out of 9, which is 1/3. Okay. What is the probability of drawing green, green, green with replacement? So we would have to use multiplication. Okay. If the events are independent, then we can multiply the probabilities together. Okay. Does the first marble influence the second marble? in this case? No. Why not? You're replacing. So they're independent. So we can do the probability of green times the probability of green times the probability of green, which is just going to be 1/3 times 1/3 times 1/3, which would be 1 over 27. Okay? I'm allowed to multiply because they are independent. The first one does not affect the second one. Okay? All right. What is the probability of green and then blue without replacement? Does the first one affect the second one? Yes, it does. So the probability of green is still 1/3. The probability of blue is 4 over 9. Can I just multiply those together? No. How about 8? Well, sorry. So the overall probability of green is 1/3. The overall probability of blue is 4 over 9. But can I multiply those two together and get the right number? No, because does the probability of blue depend on the probability of green in the first roll? Yes. So what we do is this. The probability of green is 1/3. And then we get the probability of blue given that draw 1 was green. And this number changes the denominator. So we're going to do 1 out of 3 times 4 out of 8. So you can still multiply if they're dependent, but you have to make that second multiplication conditional. It has to be influenced by the first. Okay? What is the probability of drawing red, red, red without replacement? 0. It can't happen. We ran out of reds. Okay? All right. What is the probability of at least one red in 4 draws with replacement? Now that's really complicated. We would have to find the probability of getting all 4 reds, and then the probability of getting 3 reds, and then the probability of 2 reds and 1 reds, and add them all together. Do you guys remember the at least one trick? 1 minus. So instead of calculating the probability of winning, let's calculate the probability of losing. So what is the probability of not red? Would be 7 out of 9. So the only way to win here is somewhere in the list there's a red. So we're going to be generating these four letter words, right? If there is an R somewhere in there, you win. So the easiest way to calculate this is find the probability of no R's anywhere. And that would be 7 out of 9 in the first one. Is the second draw influenced by the first draw? No. So losing in the second one is still 7 out of 9. And then the next one would be 7 out of 9. And then the next one would be 7 out of 9. We multiply all those together, and that would be the probability of losing. So the probability of winning would be 1 minus all of that. Okay? When can you add probabilities? So ands are multiply problems. So when we did the probability of green, 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 this is green and green and green. And statements mean multiply. When can you multiply? When they're independent, you can multiply. When they're dependent, you can still multiply, but you have to change those conditional probabilities. Okay? What if it was or? So what is the probability of green or blue in one draw? Well, the probability of green is 3 out of 9, and the probability of blue is 4 out of 9. And I want to add those together. When are you allowed to add? When they are mutually exclusive. Okay? You can add when they are mutually exclusive. What does that mean? Mutually exclusive means that the first one prohibits the second one. Does drawing a green prohibit you from drawing a blue? Yes. So you can add them. So this probability is going to be 7 out of 9. Okay? But let's say I had a box with people. So let's say we have a girl who plays well, let's not do that. A girl who plays basketball and a boy who plays basketball and a boy. This is not going to work. The commas are going to mix me up. Okay. So a girl who plays basketball and a boy who plays basketball and a boy who wrestles and another boy who wrestles and a girl who wrestles and another girl who plays basketball and another boy who wrestles. Okay? What is the probability of drawing a girl or a wrestler? Does being a girl prevent you from wrestling, from being a wrestler? No. So, can we just add? So there are 3 girls and 4 boys. So can we just add 3 over 7 plus 1, 2, 3, 4 out of 7 are wrestlers? Will that work? No. Why not? Is the answer 7 out of 7? No, obviously not. That would be a guarantee. So what is the actual probability of, this should say or. What is the actual probability of drawing a girl or a wrestler? Well, look up there. How many would that include? So it would be this one, this one, this one, this one, this one, or this one, which is 6 out of 7. Why is this number wrong? Yep, that girl wrestler got counted twice, right? So there's one person in there that is a girl and a wrestler. There is one person in here who is a girl and a wrestler. So if I went like this, let's number these. So person 1, 2, 3, 4, 5, 6, and 7. So if I say girl and wrestler, person 1 goes in here. Person 2 goes in here. Not a girl, not a wrestler. What about person 3? Wrestler but not girl. Person 4? Wrestler but not girl. Person 5? Girl wrestler. And person 6? Girl but not wrestler. And person 7? Wrestler but not girl. Okay? So if I want girl or wrestler, then I'm looking at this. Right? So If they are mutually exclusive, then all you have to do is add the probabilities together. But what if they're not mutually exclusive? Then you add the probabilities together and you subtract off the intersection. So this girl got counted twice, so I need to subtract her off, and that's where the 6 out of 7 comes from. Okay? So if they are independent, you can multiply for an AND statement. If they're not independent, you can still multiply, but you just have to use conditional probabilities. If they are mutually exclusive, for an OR statement, you can add. If they're not mutually exclusive, you can still add. You just have to subtract off everybody that got overlapped. Okay? So let's say we had men and women, vanilla and chocolate ice cream. Let's make this easy. 20, 30, and 10, 40. Okay. What is the probability? So that total is 100. What is the probability of picking a male? %30. So I talked to 100 people, asked them, are you male or female? Do you prefer vanilla or chocolate ice cream? Okay. What is the probability of male and chocolate? What would it be? 10%. So the probability of male is 30%, and the probability of chocolate is 50%. Can I do 50 times 30? No, because they are not independent. Right? Does your preference of ice cream depend on your gender? Yeah, it's pretty obvious that it does. So they are not independent, so you can't multiply. So instead, you just pick that up. Okay? What is the probability of women given vanilla? So this is 50%. What is the probability of drawing a woman knowing that you are only looking at the vanilla likers? It would be 30 over 50, which is 40%. So given means I'm only allowed to look here. It's like I draw a person out and I tell you this person is a vanilla liker. What is the chance that that person is a woman? Be 3 out of 5 for 40 or 60%. Okay. What is the probability of vanilla or woman? So can I just add the women and the vanillas? No, why not? Because there are 30 people who are vanilla women. So we would have to do 70 plus 50 minus 30, or you could just add all of those together. We good? All right. Boy, that takes us vanilla women. Okay, before we move on to hypothesis testing, the best kind of sample is a simple random sample. Some examples of bad sampling would be not cluster, but quota sampling. Quota sampling is where you go out and you have to have this many white people and this many black people and this many women and this many old and young, and that's just a bad idea. There are lots of different ways to do simple random samples. One is you give everybody a number, and then you count off 1, 2, 3, 4, 5, pick that person, 1, 2, 3, 4, 5, pick that person. You could use a random number generator. Cluster sampling works pretty well. So that is where you divide your area into specific pieces of equal size, and then you choose 2 of those 10 pieces. And then you take each of those 2 pieces and you divide them up into 100 pieces, and you take 10 of those 100 pieces, and then you get down to the neighborhood level, and in those 10 pieces there are 50 houses in each, and you talk to 30 houses in each of those groups. And as long as the selections are random, that actually does a pretty good job of doing sampling. Different examples of biases. If you send out 1,000 surveys and only 5 come back, you are probably subject to a bias called non-response bias. Okay. Boy, there's so much to go over. All right, let me go to 1, 4. No, 6, 4. All right. Oh. Oh, that's not it. Okay. Histograms. When we draw histograms, let's say I'm looking at dollar values. So from looking at the people who make how much they make per hour. So 0 to 10, I have 8 people, $10. From 10 to 20, I have $20 an hour. I have 24 people. And from 20 to 40, I have 16 people. And from 40 to 55, I have 20 people. How would I draw this histogram? Well, 10, 20, these need to be evenly distributed. 30, 40, 50, and 60. And then I'm going to put a mark at 55. Okay. So how many people are there total? There are 68 people. So 68, so 8 divided by 68 is, ooh, that's ugly. Let's not do 68. Let's do, let's change this to 12. What was it, 16? So let's do 30. No, 28. All right, 8 plus 24 plus 28 plus 20 is 80. So 10% of the people are here. 30% of the people are here. 28 divided by 80. 35% of the people are here. And 20 divided by 15. Nope, that's not right. How about 15 divided by 20? No, how about 20 divided by 80, which is 25%. There we go. Okay, does that make sense, what I did? So how do we draw the histogram? Well, I need the heights. How big are the heights going to be? Well, the y-axis, which is the heights, are going to be in percent per dollar. So I know that this box here has to equal 10%, right? But how wide is it? It's 10 units wide, which means the height of this box is going to be 1. This box contains 30%, but it has a width of 10, so 30 divided by 10 is 3. This box has a width of 20 and an area of 35, so 35 divided by 20 is a height of 1.75. And this has a height, or sorry, an area of 25 and a width of 15. So this is 1.66. So my highest box goes all the way to 3. So this one has a width of 10 and a height of 1. And then the next one has a width of 10 but a height of 3. And the next one has a width of 20 and a height of 1.75. And then the next one has a width of 15 and a height of 1.6. And that's my histogram. So the size of the box is the area, the percentage. And you take the percentage and divide it by the width to figure out the height. Okay? All right. Hypothesis testing. So let's say I make a claim that the average height of males at Emory High is 71 inches. And you go do a survey and you take a sample of 144 males at Emory High, and your average for your sample is 70 inches, plus or minus, well, let's just say with an SD of 2. Does your information disprove my claim? What sort of test are we going to do? One sample Z test. Why one sample Z? This is bigger than 100, and I only took one sample. So my null hypothesis is going to say, oh, is this going to be one-tailed or two-tailed? One-tailed or two-tailed? This would be two-tailed because originally I said, I think that the true average is 71. Do you think it's anything different? So different would be two-tailed, and less than or greater than would be one-tailed. I did not ask, is the true value shorter than that? Now, you have to ask that question before this happens. You have to decide if it's one-tailed or two-tailed before you take the sample. You can't decide afterwards. Now, how would anybody know? They're not going to know. But that's a big no-no. Okay. So the null says that 71 is equal to 70. And the alternative says that 71 is not equal to 70. And let's use alpha equals 0.05, which means a 95% window, right? So I need to put 2.5 over here and 2.5 over here. Why? Because I said equal to or not equal to. Okay? So if we land in either of these two windows, we will reject the null. Okay? All right. So I need an SE. And my SE is going to be SE average, which is 2 divided by the square root of 144, which is 12. So 2 divided by 12, and I get 0.166. So my SE is 0.166. Okay. So I expected 71, and I ended up with 70. So 70 minus 71 is negative 1, divided by 0.166. So I need to shade norm from negative infinity to negative 6. Am I going to land in this negative 2? the 2.5 window on the left side? Yes. How much area is to the left of -6? None. None at all. Okay. Let's do something similar. I'm going to claim, well, let's do something totally different. So I am making some kind of drug. Okay? And I want to sell it for millions and millions of dollars. But I'm going to compare it to a drug, to a placebo. Did I mess up? Oh, okay. So I'm going to issue drug A or the placebo. Okay? And I want my drug to be better than placebo. Okay? So we give these a score, and the placebo scores a 56 with an SD of, 7. And my drug scores a 59 with an SD of 6. And I did 121. My sample included 121 people. Okay. What sort of test am I going to do? 2 sample Z, right? Neither of these are assumed to be true. So this is a 2 sample Z test. So my null is going to say that the difference is equal to 0. And my alternative is going to say that the difference is greater than 0. Is this going to be a one-tailed or a two-tailed test? One-tailed, because I wanted to know, is my drug better than a placebo? All right. So I need SEs. So I divide this by the square root of 121 and divide this by the square root of 121. So 6 over 11 and 7 over 11. Okay. Now what? 2 sample Z test. I need SE difference. So the square root of 0.545 squared plus 0.636 squared. So my SE for difference is 0.84. I'm going to change this. Sorry. I want to say 50. I want 58. Okay. So what is my actual difference? I expected a difference of 0. What is my actual difference? 1. So the placebo scored a 58. My drug scored a 59. So 1 plus or minus 0.84. So 1 divided by 0.84 is a z-score of 1.19. And I'm testing this in a 5% window. So I'm going to take my shade norm, and I'm going to shade from 1.19 to 5. Oh, that's not going to work, huh? And I get a p-value of 12. Well, 12 is bigger than 5, which means we accept the null, which means there's not enough evidence to say that my drug was better than a placebo. Now, did my drug score better than the placebo? Yes, but that difference can totally be explained by chance. Okay. All right. What if I told you that the percentage of males in Emery County is 40 43%. My claim is Emery County is 43% male. And so you run out and you do a survey and you get a male. So this is my claim and this is your sample. Your percentage of male that you get is 46%. And you talked to 49 people. Okay. So we need an SD. Which one of these do we use for our SD? The sample or the claim? Always use the box unless you don't have it. So we are assuming that this is the box. So the SD is going to be 1 minus 0 times the square root of 0.43 times 0.47, which we know is going to be 0.499. The good thing is if you mess that up, it's not going to matter too much because this is really close to that. Okay. So with an SD of 0.5, what is my, oh, now what? Not yet. What sort of test are we going to do? We are going to do a one sample t-test. Why a t-test? Because the draws are less than 100. And whenever I have draws less than 100, I'm not quite sure of my data. So I need to inflate this a little bit using the SD plus formula. So we take the SD and we times it by the square root of d over d minus 1. So 0.5 times the square root of 50 divided by 49. And that will inflate my SD just a little bit. It didn't have much of an effect in this case. Okay. So now I need an SE for average. So I'm going to divide that by the square root of 81. Nope, 49 was my number. And I get 7.2%. Okay. So my null says that 43 is equal to 46. My alternative says, was this one-tailed or two-tailed? This one was two-tailed because I said my claim is that the percentage is 43%. Am I right or am I wrong? Right? That would be, I could be high, I could be low. So remember, when you do a two-tailed test, we put 2.5% on each side. Okay. The alternative says that 43 is not equal to 46. So, I guess here's my normal curve. 43 goes in the middle, plus or minus 7.2. And 46 is right here. So 46 minus 43 is 3 divided by 7.2 is 0.41. Now I shade norm from 0.41 to 5. And I get 34%. 34 is bigger than 2.5, which means I accept the null. I failed to reject the null, is how a lot of statisticians like to say it. Okay. What if instead of 46 I had 53? So let's change this to 53. So that's 10. Ooh, let's not do that. Let's do 55. So if I draw a line here at 55, 55 minus 43 is 12. 12 divided by 7 is 1.74. So I'm going to shade norm from 1.74 to 5. Okay, and I get 4%. So this area here is 4%. Do I accept the null or reject the null? I accept because 4 is bigger than 2.5. If this was a one-tailed test, then I would reject the null in favor of the alternative. Got it? Do you want to see a chi-squared? Okay. What? Like when you what? Well, let's just do one from the finals. I'll do that together. But do you want to review chi-squared? Yes, no. Maybe wait a day and see. Okay. All right. Video 2 is over.